Hello everybody and welcome back. Root Beer here with question number 5 on the 2003 Euclid paper. Hopefully you've had a chance to take a look at it. If you haven't, download a copy of the contest by clicking the link in the YouTube description and give it a shot for yourself. It's got a light bulb part and it's got a written part. And we're going to go through it now. Obviously if you want to try it, pause the video and then resume whenever you are ready to see how I handle it. So, our light bulb question A. In the series of odd numbers 1 plus 3 plus 5 minus 7 minus 9 minus 11 plus 13 plus 15, so it looks like we got 3 positives and then 3 minuses and 3 positives and 3 minuses, and they're just doing all the odd numbers. Okay. Oh, they tell us that. The signs alternate every 3 terms. Okay. What is the sum of the first 300 terms of the series? Okay. First 300 odd numbers, so I guess that would go up to, 599. That's, I guess, would those be pluses or minuses? Well, I don't, off the top of my head, know an answer to this one. It's a sequence or sort of a sum of a given sequence. Well, not just a sum, it's also some differences in there. So there might have been a formula, but I don't know of one off the top of my head. So what I'm going to do is I'm going to just take a look at this and just try and investigate it out, see if I can find some patterns, maybe, and we'll see where we can go from there. Okay. So what is it? It's 1 plus 3 plus 5, minus 7, minus 9, minus 11, plus 13, plus 15. Yeah, it was every 3 it alternates sign, and so on. Now, because we obviously already have sort of groups of 3. That group of 3, that group of 3. I'm thinking we should probably take a look at these and not individually look at 1, and then 1 plus 3, and then 1 plus 3 plus 5, and then 1 plus 3 plus 5 plus 7. I'm thinking we might want to look at this in groups of 3, or maybe groups of 6, maybe, just so that we're back to the pluses. These are certainly possibilities. These are just things I'm thinking of based on the layout, on the pattern that I'm seeing. So if I were to do 1 plus 3 plus 5, I know that that's 9. And then minus 7, minus 9, minus 11. The 9 and the 11 become 20, so this will be minus 27. Maybe multiples of 9 in some meaningful way. 13 plus 15 plus 17. You know what? It's 3 times the middle number. Because this is 2 more than the middle number. This is 2 less than the middle number. So this will be plus 45. Okay. And then the next one will be 1921, so it'll be minus 63, I guess. I noticed that we have a factor of 9 here. So I can take that out, and I notice I've got 9, 1 minus 3, plus 5, minus 7, probably plus 9, and so on. So that's certainly something. And if I were to add this up, something I'm seeing right away here is that the difference between any 2 is just, well, it's negative 2. So I'm going to have 9 times and then a bunch of sums of negative 2. How many of these negative 2's am I going to get? Once I know that, then it's just a quick grab of the calculator and we can work out our answer. But already, since I know we're adding up a bunch of negative 2's, I should be looking at for a negative number that's a multiple of 9 for my answer. Okay. So how many 2's? There's 1 minus 2 for each pair of these, and each pair of these corresponded to 3 of these. So each 6 terms in our sum. Okay, now we're adding up the first 300 terms. So how many minus 2's do we have? 300 over 6, 50 minus 2's. So our total is going to be 9 times 50 copies of minus 2. We'll bring the minus in front. We got 9, and then we got 50 times 2. That's 100. So we're looking at negative 900. And although it's a light bulb question, we've shown a little bit of our workings. We have some statements here. So even if minus 900 wasn't right, and it was something else, like maybe I got that 50 wrong, and maybe it should be 60 or something like that, then I would still get part marks because my reasoning is there. So maybe this question's out of 3. I might get 2 if I were wrong. But I'm pretty sure we're right with the negative 900. So let's move on to 5b. A 2-digit number has the property that the square of its tens digit plus 10 times its units digit equals the square of its units digit plus 10 times its tens digit. Okay. Determine all 2-digit numbers which have this property and are prime numbers. Okay. So this and our prime numbers thing is probably a little important. One thing you could do, because we're just considering 2-digit numbers, is there's only I believe it's 25. There are 25 primes less than 100. So there's got to be. I mean, there's 2, 3, 5, and 7. So there's 21 2-digit prime numbers. You could probably list them all out and make a couple columns and do square of the tens digit plus 10 times the units digit, that sort of thing. And you could probably make a little chart in your notebook and get this question done. And that's one way to do it. I think that's a little exhaustive. I think we can use the property that they've given us to narrow it down and then say, okay, which of these possibilities is prime? That's just my thinking right now. So we're talking about a 2-digit number. There's a really nice way to write out a 2-digit number. This is great for proving things like divisibility rules. And any 2-digit number can be written like this. 10a plus b, where a and b are single digits. So, for example, 19, a would be 1 and b would be 9. Or for 43, a would be 4 and b would be 3. And we do this because now we've singled out a and b. They are the digits that make up the number. Okay? So when they say, what is it, because it was a wordy little property, the square of its tens digit plus 10 times its units digit, we can express that now. The square of its tens digit plus 10 times its units digit. B is the units digit, A is the tens digit. Is equal to the square of the units digit plus 10 times its tens digit. So square of the units plus 10 times A. Alright. So this is a very symmetric looking equation. And one thing to note about symmetric equations is usually you can work them out so that they have a factor, sort of an a minus b, because the a's and the b's, they can very easily swap. If a were b, it's very obvious that this equation would be satisfied. So a minus b is probably a factor of some rearrangement of this, and that's what I'm going to go for. Let's bring it all to one side. So minus b squared. I'm keeping these two together. It's a difference of squares, so I can factor that really quickly. Plus 10b, and then we minus the 10a. So that's all equal to 0. Now this, as I just said, is difference of squares. So we got that going on. And this, I did a minus b, so I got to be careful here. But it's minus 10 a minus b. And now I've got this a minus b. and it's a factor of both of them, so I can pull that out. And then I have a plus b minus 10. So in order for our two-digit number to have this property, the a and b, the 10th digit and the units digit, have to satisfy this equation down here. But these are all integers, and a product of any two integers being equal to 0 means one of the two terms in the product has to be equal to 0. So either a minus b is equal to 0, or a plus b minus 10 is equal to 0. And another way to say this one is a plus b is equal to 10. Oh, I guess since it's written, I should probably have a full sentence here. Let 10a plus b be our two-digit number. For a second there, I forgot it was the written style question. But so. And another way to say that a minus b is equal to 0 is just to say a is equal to b. So to have the given property, either the tens digit and units digit are equal, or they add to 10, possibly both. 55 would do that. Okay, so we can get two lists of numbers that satisfy these. All right, we can either have sort of our list where a is equal to b, and we'll get a list of 10-digit candidates here. 22, 33, 44, 55, and you can check each of these numbers satisfies the conditions in the question, but only one of them is prime. We'll use green. Okay, now we had another way to satisfy this. A plus b is equal to 10. Okay, we have certain numbers that satisfy that. 19, 1 plus 9. 28, 37, 46, 55 again, 64, 73, 82, and 91. Okay, so out of here, we just need to pick our primes. 19 is a prime. 28 isn't, it's even. 37, that's a prime. 46, not. 55, that's a multiple of 5, so that certainly isn't prime. If it were, we would have had it on we would have circled it on the other list. 64, definitely not a prime. 73, that one is a prime. 82, not a prime, it's even. And 91, it's not a prime. However, I would like to make a note, occasionally when we're marking things, or just occasionally when I mark people in general, and it's a question involving primes, there's two really high up primes, numbers that aren't prime, that sometimes people think are primes. Okay? And those two are 91 and 93. I've seen people think both of them are primes. Now 93, it should be more obvious that that is not a prime, just because it's a multiple of 3. 9 plus 3 is 12, that's a multiple of 3, so 93 must be a multiple of 3. And more specifically, it's 31 times 3. But sometimes people make the mistake. They don't really make the mistake on 95, obviously, or 99. And 97 itself is a prime. 91, however, is a little harder because it's not obvious that it's it's not a multiple of 3 that's staring you in the face. But 91 is actually 7 times 13, and it's a good one to remember, because sometimes, if I were doing this really quickly, maybe I would think 91 is a prime. And it's a good idea to know your primes up to 100. 200 may be ideal, but 100 definitely. And to especially know that 91 and 93 are not primes, because when you're getting up there high, you sometimes forget, and it's not readily apparent that, oh yeah, 7 times 13, because those multiplication tables come up so often. That sort of thing. Okay? So we have our list here. All that's left for us to do is to sort of make a concluding statement. We wanted the numbers, right? Not the determine all 2 digits. Okay, so we don't just need to say 4. So the possible 2-digit numbers are 11, 19, 37, and 73. Okay. And yeah, I think that does it for question number 5. I liked it. Hopefully you did. And in the next video, we're going to take a look at question number 6 on the 2003 Euclid. So I'll see you there.